Hi and welcome to this part 2 on our revision for Newton's laws. Okay, so this video is the one that is going to be focusing on Newton's second law. So let us get right on to it. So we're going to look at Newton's second law, do some examples, and yeah, just get it done with. So this is how we define Newton's second law. So we say when a net force acts on an object, the object will accelerate in the direction of the force, and the acceleration is directly proportional to the force and inversely proportional to the mass of the object. So this is how you write your your F net is equals to mass times acceleration formula, but it actually comes from this, and this is actually your Newton's second law equation. So let us just go through it again. When a net force acts on an object, the object will accelerate in the direction of the force, and the acceleration, let me just highlight there, the acceleration is directly proportional to the force, okay, and inversely proportional to the mass. Okay, so that is that whenever a net force occurs. I'm not going to go through this again. So, but with regards to Newton's second law, we'll be dealing mostly with this. Okay, so we're going to be looking at these forces, except for air resistance and spring forces. We have already defined frictional force. I'm actually going to remove this. Why should I keep this? Okay, I'm not going to remove this. Why am I not removing it? Okay, so in the previous video, we have defined frictional force and explained what the static frictional force is and the kinetic frictional force is. Okay, so what I'm going to do is, if you have not looked at that video, you can look at the definition and memorize it from here. But I'm just going to proceed, and we go to frictional force coefficients. So there is a way in which we find this the static frictional force and the kinetic frictional force if we are not given the values. Okay, so for static friction, the force can vary up to some maximum value. When that maximum value is surpassed, then the object will start to move. So we say the static frictional force maximum is equal to mu s times n, which is the normal force. Okay, when the applied force is greater than the maximum static frictional force, the object will move but still experience friction. This friction is called kinetic friction, and kinetic friction is given by this equation. Fk is equals to mu k times n. N is the normal force. Okay, so I'm going to do this example. So this is how we find the value of the maximum static frictional force. So we have a scenario here. To say a box is resting on a horizontal surface and has a mass of 12 kgs, and the coefficient of static friction between the surface and the box is 0.3. What is the maximum static frictional force? Okay, so what is the maximum static frictional force? So we are only given the coefficient, but we are not given the frictional force. So we need to get the frictional force. Okay, so this is our scenario that we have. We have a box which has a mass of 12 kgs. It's simply resting on the surface, and the surface has a coefficient of static friction that is equal to 0.3. Okay, so what is the maximum static frictional force? So this, if I were to apply
a force to move this box, I would need to apply a force greater than the maximum static frictional force. Okay, so we know our equation to be like this: Fs max is equal to mu s n multiplied by n. N is the normal force. So how do you get the normal force? So let's just draw a free body diagram of what we have here. So we have the weight going down like this, and we have the normal force going up like this. Okay, so in this instance there is no horizontal force acting because it's not moving, it's at rest. Okay, and our concern will be vertical motion. So we are going to say the weight will be equal to the normal force. Okay, so the reason why this will be so is because they are balancing each other out. Okay, and we know that the weight is equal to mg, right? Therefore the weight is equal to 12 times 9.8, which is 117.6. Therefore n is equal to 117.6 newtons. Okay, so we can say 0.3 multiplied by how much? The value that we have here, 117.6, and we get our Fs max as 35.3 newtons. Okay, so this is how we could get our Fs max. The next example will be this scenario, but on an inclined surface.
So this is the same example, but now we are looking at an inclined plane. So say a box is resting on an inclined surface and has a mass of 12 kgs, and the coefficient of static friction between the surface and the box is 0.3. What is the maximum static frictional force? The angle of inclination is 30 degrees. Okay, so in this case we have a plane which is no longer horizontal but rather inclined. So you will see what the difference is between that example and this example.
So we have this kind of a scenario now, 12 kgs. Okay, the coefficient is how much? It's still 0.3, but we have now an angle incline. So this box is stationary there, even though the like one would assume that maybe it might slide down. It's just stationary because of what? There's a friction, a static friction. Okay, so but we need to find that value. What is the maximum before it can start moving? So what we're going to do is we're going to draw a free body diagram of this. But first, let me just write the equation. So the equation remains the same. Okay, so this is still the equation, but in the free body diagram, we're going to realize something. So we have the box here, right? This is the weight. The normal force, instead of going like this, it's now going like this. Okay? And because it's going like this, you'll then notice that we can't really say that N is equal to W. You see, they're not all in the vertical. So what we're going to do is we're going to resolve this into its components. So we're going to have, okay, so this is the weight, right? This is the weight. Just writing it down here. This is the weight. So what we're going to do is we're going to say, let it have a component that is going like this and a component that is going like this. So we're going to have a component like this, which we're going to call it the perpendicular component of the weight, and a component like this, which we're going to call the parallel component of the weight. What is it parallel to, if you may ask? So if the weight is like this, and this is like this, and this is like this, so this component is parallel to the slope, and this component is perpendicular to the slope. Okay, so once we have that done, we'll find that this component is the one that is going to be equal to the normal force. Okay, we're going to have N is equal to N, not M. N is equal to the perpendicular component of the weight. Okay, so but we need to find its value. So okay, what we're going to have here is that we're going to have this angle. So this angle would be what we have here, and the weight we can actually calculate it. It's 12 times 9.8, right? That's the weight. which is 117.6. Okay. Another thing here is that this is 90 degrees. So if you have a right angle triangle, you can just use your trigonometry to do the following. You can say, so I'm simply just going to say cos 30, and I say cos 30 is what? Adjacent, which is this all over 117.6. Okay. Therefore, the perpendicular component is equal to what? We do this with the calculator. So, okay, first let's do this. We're going to have 117.6 cos 30. And then we're going to get a value of 101.84. You see? So this is going to be our normal force. Therefore, we can say the normal force is 101.84. And once we have this, we can substitute it here. So we're going to say Fs max is equal to 0.3 times 101.84. And how much is the final answer? We get our answer as 30.5, actually 30.6 newtons. And that's our final answer.
Okay. So it's going to be important that for the questions that we're going to do, you revise the following. Revise force diagrams and free body diagrams, doing them in different scenarios, finding resultant forces. So after you've found your free body diagrams, you should find resultant forces in either the horizontal or the vertical, and also force components. So this is mainly when you have either an inclined plane or an inclined force. Okay, you need to know how to resolve it into forces. Okay, so let us now have a look at these examples as well. The first one, a boy pushes a shopping trolley with a weight due to gravity is 250 newtons with a constant force of 90 newtons. A constant frictional force of 40 newtons is present. A. Draw a labeled force diagram to identify all the forces acting on the shopping trolley. B. Draw a free body diagram of all the forces acting on the trolley. C. Determine the resultant force on the trolley.
Okay, so for A, a labeled force diagram to identify all the forces on the shopping cart would be like this. So since it's a force diagram, you can just draw it as a block, and then we know that there will be the weight going down, normal force going up. Actually, normal force should be from here because it's exerted by the surface, okay? And then the weight can be from the middle of the box because there's something we call the centroid. So the weight actually is exerted from the center of the mass, okay? And then there's a constant force F, okay, of 90 newtons. Let's just say it's F applied actually. F applied. And then there's a frictional force, Fr. So this is how we would do the first question. And then now, the second one wants the free body diagram. Okay, so for a free body diagram, what I'm just going to do is I'm just going to erase the box and have a dot here. Okay, and extend this towards the dot. Then fix here as well. You can just align this. So the forces are still the same, but now we have a dot here instead of a box. Okay, then determine the resultant force on the trolley. Okay, so for the resultant force, I'm going to do it this way. I'm going to determine F resultant in the vertical, and I'm going to determine F resultant in the horizontal, because these two, there is some sort of a resultant force that acts on it. So for this one, we can say up is positive. Let's say up is positive. Okay, up is positive. So what we then have is, so we know that the resultant force is always equal to the mass times acceleration. Okay, so after this we can say, okay, the F resultant is equal to the normal force minus the weight, which is equal to ma. Okay, what is the weight? We are told the weight is 250 newtons. Okay, so the weight is 250 newtons, and in this case the weight is equal to the normal force. Okay, because this box is not moving up or down, so it means that the force is, okay, got it. So it means that the force is balanced out. So we'd have 250 minus 250 is equal to ma. Therefore, F resultant in the vertical is equal to 0. That is the resultant force in the vertical. Then let's move to the horizontal. So for the horizontal, what we're going to do is we're going to say F resultant, or F net. So F net and F resultant are one and the same thing. F resultant is equal to ma. Then we say let right be positive. Okay, therefore we have Fa minus Fr is equal to ma. The applied force is 90 newtons. The frictional force is 40 newtons. Therefore, F resultant in the horizontal is equal to 50 newtons. So that is how you would find your resultant forces. Let's go to the next example.
Second one. A donkey experiencing a gravitational force of 1,800 newtons is trying to pull a cart, force due to gravity of 800 newtons, with a force of 400 newtons. The rope between the cart and the donkey and the cart, makes an angle of 30 degrees with the cart. The cart does not move. How? Okay. Draw a free body diagram of all the forces acting on the donkey. Draw a force diagram of all the forces acting on the cart. Find the magnitude and direction of the frictional force preventing the cart from moving.
Okay, so in this example, there's something important I want you to realize. So even though a force is being applied to the cart, the donkey is applying a 400 Newton force. The cart does not move. So what does that mean? That means that the force that the donkey is applying is not enough, to overcome the static frictional force that is acting on the donkey, on the cart, I mean. So the cart, there is some sort of a maximum static frictional force that must be overcome first before the cart must start moving. Okay, let us do A. So the free body diagram of the forces acting on the donkey. So say this is the donkey, and then the forces that are acting on the donkey are obviously these first two are obviously there, the weight and the normal force. And then there is the force that is applied at an angle, the force that it is trying to push or to pull the cart with, which will name it the tension. Okay, so this is one way of writing the free body diagram for the forces. But the other possible way you could write is like this. So this is the weight, the normal force, and then you say it's T in the x direction and it's tension in the y direction. Okay, I hope this doesn't raise any questions. We've just resolved this into its forces. Okay, and in our case, so Tx, let me just write here. Tx, which would be this one, it would be, so the angle is here. So it would be T cos 30, while Ty would be T sine 30. Okay, I hope this is clear. Let's go to B. So B, let me just erase this. I'll keep this as it is. draw a force diagram of all the forces acting on the cart. Okay, a force diagram acting on the cart, of forces acting on the cart. This is your cart. There is the weight. Normal force is the friction. There should be friction if this thing is not moving. Friction, and then there is the tension force. You see. So this is one way of writing it, but I would recommend that you resolve it into its components. So you'd have Tx and you'd have Ty. Okay. So this is what you'd have as the free body diagram of the forces that are acting on the cart. Now number C, find the magnitude and direction of the frictional force preventing the cart from moving. Okay, so let me just keep this as it is for now. Okay, so we are told that the force that is applied is 400 newtons, right? So this is C. T is equal to 400 newtons. And for us to find the frictional force, we would have to deal with forces in the horizontal direction. Therefore, Tx we can say it's equal to 400 cos 30. How much is this? This is equal to 346.4 newtons. Okay, and then after we have done that, we can say F net is equal to MA. Force is in the horizontal, and then we say let right be positive. Okay, let right be positive. So we can say, okay, our F net is comprised of Tx minus Fr, not Fx, is equal to Ma. But what is the acceleration on this box? Because it's not moving. We know that our acceleration is 0. What is Tx? 346.4 minus Fr. What is the value of the friction? It is equal to 346.4 newtons. And then we are required to also mention the direction. So the direction, since right is positive and we inserted this as negative, it means the friction force is going to the left. And that is example 4.
So these are the 3 papers which I recommend for you to practice with. I'm going to upload videos whereby I work through this question papers, but try them before you look at the solutions. Okay, so it's the February, March 2018, November 2015, and May, June 2017. Thank you.